Our meetup tonight. For some of you, it might have been a long trek. For us from San Mateo, it was pretty quick. Thankfully, there's no traffic. As you guys all saw, there's pizza and drinks outside. Feel free to grab stickers and mints and things. I'm Adam. I work for Neo Technology, creators of Neo4j. Can everyone who works with Neo4j raise your hand? Awesome. And then the organizer of this event was the Berkeley Graph Visualization Group, which was organized by Sylvia and the Tom Sawyer crew. Can you guys raise your hand? Awesome. Well, so you guys know who's running the show, so feel free to ask us any questions after. Just wanted to plug a few quick things. One, as you guys can see on the screen, Graph Connect. It's the largest conference on graph databases and graph applications. It's coming up on October 22nd, and you can sign up for I think it's 99 bucks, but I'll make sure it is after this meeting. With SF Local 200, the discount code. It's going to be a packed day of talks, and then the day before we'll be having some trainings. So I highly recommend checking that out. And yeah, and also we have a ton of meetups going on all the time, so we hope to see you at one of those as well. Without further ado, I'd like to introduce Nicole. Nicole White works at Neo as our data scientist. She's done a lot of awesome projects with data science and Neo4j, and she's here to talk to you a little bit about what Neo4j is and how to use a graph database before Josh talks about how do you visualize a graph database. Right, Nicole?
Thank you, Adam. Right, so today I'll be doing a brief abbreviated intro to Neo4j, and that will include what is a graph, what is Neo4j, a quick data modeling, a journey from SQL to graph, and then a quick demo of our browser tool. So what is a graph? We have a pop quiz to start this out. Are these graphs? We're going to take a stab. You guys saying yes?
Yes and no.
No, it is not a graph. This is a graph. When we talk about graphs in Neo4j, this is what we're talking about. And in its simplest form, it's a set of nodes that are connected by relationships. All right, so what is Neo4j? Neo4j is a graph database. And that is in the NoSQL category. NoSQL either means not SQL or not only SQL, depending on who you ask. And Neo4j was founded in Sweden. So here we have a graph that looks kind of like what I just showed you guys, but perhaps we might want to say more about these entities. And when I say entity, I'm referring to nodes and relationships. So we might want to say that the language property on the Sweden node is Swedish, and that Neo4j open source is true. And we might want to put a property on the relationship saying that we were founded in the year 2007. So this is the property graph, and that is what Neo4j is. It's a graph database that allows you to store your data as a property graph. And here I'm showing the properties available to you. You can have strings, numeric, and Boolean. So very quickly, I'm going to show, for people who are familiar with relational databases in SQL, a data set and how you would model it in a relational database, and then how I'd model that same data set in a graph, and some of the advantages of doing so. So, taking YouTube as an example, or really anything where users watch and subscribe to videos, if we were to do this in a relational database, we might start out with a users table and a channels table where we have just the username and the channel name. And then to say which users operate which channels or own which channels, we would maybe create a users channels table with a foreign key to, but I had more animation to, with a foreign key to the users table and the channels table, right? And then if we wanted to keep track of users subscribing to channels, we'd probably add another table, a user subscriptions channel, again, capturing how users are subscribing to channels, right? So this is a very classic way you might model this data. And if you were to ask questions like, how many channels have the word Bob in it, a relational database would be very, very good at that. But if you wanted to ask questions like, how is Charles related to David, it's kind of an arbitrary question, not very straightforward. If we look at this, it's not immediately obvious. I mean, Charles, I'll tell you right now, I know the data model. Charles doesn't actually subscribe to any channels owned by David or vice versa, but it could be possible that, through a path of user subscriptions that Charles somehow is related to David. And it's hard to see with this data model, and not unrelatedly, it's hard to express these kinds of questions in SQL. So with that, let's look at how we would model this same data set in a graph and in Neo4j specifically. Here we would start out, I have a legend up there, I don't know if you can see it. These are all going to be user nodes in blue. And then we'll have some channel nodes in green. And then we'll put properties on all of these nodes. So the user nodes would have a name property, with their username perhaps. And the channel nodes would also have a name property with the name of the channel. And then now if we want to model users operating or owning a channel, we would create these outgoing relationships, and we would assign a relationship type called operates, outgoing from user nodes to channel nodes, indicating that this user operates that channel. And if a user does not operate a channel, the relationship simply is not there. There's not a null value in any table. It's just the relationship is not there. So Alex does not own or operate any channels. Yep.
So the labels are one per node, or can there be more?
It can be more. You can, so, I mean, it isn't appropriate for this data model, but there can be more than one relationship.
No, like there was a relationship, but like the name Bob, can there be multiple
Yeah, you can put as many properties on a node that you want. You can put an arbitrary amount. You can put different properties on different nodes. So it could be the case that that node with the name Bob also has an H property, but not all of user nodes need to have that H property. There's nothing constraining that to make it true. So the properties, you can pretty much throw anything you want to add it. All right, so then if we wanted to also model users subscribing to channels, we would create a different type of relationship, and I called it subscribe, where users subscribe to channels, and that would also be outgoing from users to channels. So here we see that we have different node types and different relationship types, and we can attach any amount of properties. And now, with this data model, you can see pretty clearly, now if I ask the same question, how does Charles know David, or how is Charles related to David, we can see in a few ways how they are connected. You can see that Charles subscribes to a channel that is operated by Bob, and Bob is subscribed to a channel that is operated by David. And that's a very simple query to write in Neo4j in our Cypher query language, which I'm not going to get into today, but there's a way on it. And then real quick, if I have it, let me check. Our browser, this is where you can test Cypher queries and whatnot. So this is what a Cypher query would look like. Here I'm saying, find me a pathway between Charles and David and return it. And this is what that would look like. This is actually a Neo4j database of that data I just showed you. And we can see Charles operates a channel that Alice subscribes to, and Alice subscribes to a channel that David operates. And so this is just a tool you open in your web browser, your default web browser, and you play around with Cypher queries with the Neo4j database that you have running locally or otherwise. And so that's my quick intro to Neo4j graph databases. So I'll turn it over to Josh to do the main show. Thank you.
See if technology is going to cooperate with me. That's what it does. All right, hi. So I am, hopefully, is this actually gonna work? Okay, yeah. Now Sylvia will be happy with me. So obviously I am Jonathan Feingold. I'm the Solutions Engineering Manager at Tom Sawyer Software. What that means for us, because that means different things all over the place, is that I manage things like customer support and doing demos and going out to meet customers and coming up with proofs of concept for all kinds of things. So customer-facing engineering, basically. And I'm going to be talking to you a little bit about Tom Sawyer Perspectives and how that relates to Neo4j. And so here's my contact information. J. Feingold at Tom Sawyer Software. So basically, any questions that you have for me that you don't want to ask here or that come to your mind after this, you can send me an email. Any feedback that you have about this event can go to Sylvia Chang, who is our marketing director. Sylvia, who was instrumental in putting this event together for us, and your feedback will determine whether we have more of these and what they will be like and how we change them in the future. So let's get started. So we just spoke very briefly about the Cypher query language, and here we have something that is going to be based on the Cypher query language. So let's just jump into this and pretend that we all know everything already. So here I've just launched a browser. There is, if you go to the Neo website, a whole bunch of data sets that have been used in the past and that are publicly available just kind of for people to play around with. The one we're looking at right now is called the synchronized data set. It is based on just a collection of movies and actors and directors and a bunch of stuff that all kind of fits together in this notion. And because it's Neo, we start the example with the Matrix, because, you know, Neo, right? So here, if you remember the little circles and dots that you had in the Neo browser, this is kind of a different way of conceptualizing it. On the back end, we have the same Cypher query that's running it, but the user of this application never has to think about it. So we run a Cypher query that's going to match all of our movies named The Matrix something. And we have a little exploration that we can do. So why don't I go ahead and select The Matrix. I'm going to click on this action here that says load data. And that's going to run a supplementary Cypher query. And we're going to find all the adjacent nodes, right? So just like the Cypher query, you can use the structure to find out who's adjacent to what, right? You can do the same thing here. We've loaded in a bunch of people. We've loaded in a director. We can load in some other fun facts about that director, some other movies that she directed, which happen to include the other two Matrix movies. You can load in some data about this Matrix movie, and you can see that there's, unsurprisingly, some overlap between the directors. And then maybe, you know, this is starting to get a little bit jumbled, so let's go ahead and do a new layout on that. So now you can nicely see that all the people that are shared between these films come together, right? So this fundamentally is where we're going. But I'm going to talk just a little bit about how we get there. I'm not going to go into too much technical detail because probably most of you are not terribly interested in the exact technical details of how we get here. But this is about taking a data source, could be Neo4j, could be something else, could be Neo4j and something else, and bringing it all together into a single unified data model and pushing it out into something that a person can use and understand very easily without a deep knowledge of any particular query language or database or anything like that. So Tom Sawyer Perspectives is what we use to generate this web application that you see in the background here. This is one of the components of Tom Sawyer Perspectives as well. This is the designer. This is basically just a graphical interface that allows you to define what your data looks like and what it does. And then we use that to generate an XML file that gets stored in the back end. And then you can access it to make creating applications that look like this very, very, very easy. So again, I'm not going to go into a ton of technical detail here, but just like with most databases well, SQL databases, you do define a schema, but these are just attributed objects, just like you have attributed nodes and relationships inside of Neo, right? You have a person, a movie, acts in, directed, and gender, and in fact, these are node and relationship types from Neo. Here we have an integrator. We're saying we want to bind to a Neo4j data source. This is where it lives. Here are the model element types, person. So here we actually have written a Neo query. It's going to look for a person who either directed or acts in this movie, where the person's name is what we're searching for, and then we're going to return these distinct person entities, right? So it's just writing a query, but doing it in a way that masks the end user from having to know anything about your data source. Here we get to do some cool stuff with UI. So here we get to define an actor. All right, so we have some rules that show you what stuff looks like. Now you've got a male actor and a female actor that are inherited from the base actor type. We've got a drawing where we set up rules. Let's say for each person that I find in the data backend, I'm going to create a person node. And if it's a new person node because I just loaded it, then we're going to set some properties for it, and we're going to set some layout properties for it. We can also define cool stuff like that add neighbors action. So the toolbars, we're just going to define a default toolbar where we have a whole bunch of default things like save as image. We have a search field, which I can show you in just a second. And then we have these custom find and load data actions, which allow us to explore our data using the queries that we define. Right in here, let's say I like Lawrence Fishburne. He's a pretty cool dude. He wears fancy sunglasses. So I'm just going to look for him up here. Here I've got a search. We've defined it to look under actors. We can also look at movies. So here's a matrix. So let's click on Matrix Reloaded. We can see it down here. If our screen resolution was a little better, we'd also be able to see this in Spectre. Right? I don't have internet access. Okay. So if I had internet access, these would go out and get me a movie poster and a movie rating from IMDb. Unfortunately, we don't have that yet. So fundamentally, all we're doing in Perspectives is taking data that you have, whatever data you're interested in, and we're turning it into a front end. And Neo4j is obviously a really cool way to store that data and gets you a lot of query capabilities if you're interested in types of relationships that Neo cares about. So we're going to go through some examples now that are not based on Neo, but do display capabilities that you could obviously enable with Neo. I just don't have the capability to run 600 different Neo databases on my laptop at once, so we're just going to go through them in different data formats. So here, this is actually, if you get a demo from us, or if you get an evaluation, it will come with an installer that comes with all these examples that I'm about to show you. So let's go into some industries that people who have connected data like to talk about. So here's a network editor. let's just go ahead and launch this. So this is just another configuration. I just hit launch to HTML5 preview, and this is taking that configuration that is related to, this one is actually just an Excel file, nothing fancy at all, and relating it to these front-end data objects and generating this kind of default layout with tables on the bottom, drawings, kind of taking up the bulk of it, a details inspector down on the left, and some tree controls over here, right? So let's say I'm interested in a router, right? Let's go ahead and search for a router. Now we get to watch something cool happen. So I'm going to select this router. And now we zoomed in. So we went from a very abstract view of a router with very little detail. We got close to it. It gave us more information. We also selected it in the device table because, as I talked about before, we define this data object and then we map it to drawing elements on the front end, right? So we created a node for the actor, we created a node for the router. Fundamentally, there is just a router in the data, right? We don't care that it has a node on the front end, and it's also in this table down here. It's all just the router. So because it's all just the router, it all works together automatically. So I select the router down here. It selects the router over here, both in the location where it lives and in the type category. It also brings up the details. It also shows it down in this table, all automatically connected just because it's a single piece of data, which if you're running Neo queries to get your data back is the thing you probably care about. All right, so we have this level of detail, and maybe we want to see a different route. So here's router B. We'll zoom out a bit. And maybe we want to see it in a slightly different layout. So this is a kind of a classic network layout, right? Very much akin to a force-directed layout, but a bit more complicated than that. You can also get an orthogonal schematic. We can also create a hierarchy. Here we have an orthogonally routed hierarchy, so each of these edges that connects them is a nice up and down edge up until it gets to the last bit where it can slant in. Check that out. All right, so it all comes in. Again, nice detail when you zoom in. Or we can view it as circular clusters. All right, and these are clusters that are based on the connectivity of the data. So each of these clusters is detecting a group of nodes and edges such that all the nodes have maximal connectivity to other nodes within the group and minimal connectivity to nodes on the outside of the group. Right? So again, like this is exactly why you are interested in getting your data in a graph form so that you can see the relationships that exist. And this is a layout that does an analysis for you and then makes that visual impact immediately obvious. So you can also see it a different way. So we saw that in the other view, as we zoomed in, the UI has changed. That's optional. You can simplify your project if, for example, you want very high performance and you just want very simple UIs. You can just keep them simple, or you can make them complicated. Here we're driving an entirely different topology. So we have routers that are connected to routers. Right? You can see this edge here. We have phones that are connected to routers. We have laptops that are connected to routers. And this topology is driven by the exact same data set that is driving our overall network topology. So we've got this one data set, and it's all driven by this graph that exists behind this network. But just because there is one representation of the way data is connected to other data doesn't mean it's the only representation. And this gives you the power to view that however you need to view it. All right, so let's jump to a different example. So we talked very briefly about having circular layout reveal some information about the analysis behind it. So what I'm going to show you right now is a microwave transmission network for cellular data. This is not real data, but it is proof of concept that we developed for a real application that handles cellular networks. And so I've been launching to the HTML5 preview, which goes directly into a browser. Now I'm going to launch the exact same application, but into a desktop preview. So one of the nice things that Perspectives does is it lets you do all of your development of figuring out how your data is related to your data, what you want to see, whether you want tables that are connected to drawings, if you want drawings that are connected to other drawings, and then at the very end, you get to decide, do I want this to be a web application? Do I want it to be a desktop application? Do I want it to be both? Do I want it to be some mixture of the two that interconnect, right? So this is doing the exact same procedure of generating a default layout of all of these devices, we're just putting in a desktop front end. And we can also do this with .NET if you're interested in .NET. So let's take a look at this data. I'm going to zoom in here and kind of check this out. So we have a bunch of edges here. And remember that edges can be attributed, just like nodes can be attributed. And so we have a bunch of connections that have a total bandwidth, right? So we have a total available bandwidth. So capacity is 16, and the requirement is the usage. It's using 14 of its 16, I forget what the unit is for this example. But you can see that it's kind of this dark red color and it's a relatively thin line. Over here we have a capacity of 24 and a requirement of 12, so it's only a 50% utilization. That's good. So that edge is showing up in green and it's a little thicker. We can find some really highly utilized edges down here in dark red, and some very high capacity edges over here, just based on the thickness. So we're able to use visual cues as well as, inspected details data, right? So if we click here, I can get all of this in exact detail of, the total bandwidth available, the phase, all the specifications on this connection. But at the same time, I can just look at it and see obviously, oh, this is very low utilization because it's purple, and this is, a very high bandwidth because it's thick. The other cool thing is that everything is data driven, like I said. It's all coming from a back end, it's just based on rules. So every component of this UI is also just driven by data. And this is a purple edge because it's not being utilized very highly. So let's just double click on this and we'll choose, maybe purple isn't the color I want. I want to see the edges that aren't being used to kind of fade into the background a little bit. So we'll make it a very light green. And now this will interpolate this color from 0 utilization up to 50% utilization, and then 50% to 100%. And this is all just changing the data that drives the visualization front end. And if you have multiple users, you can store their preferences back to the data source because it's just data. Yeah?
Is it possible to add a timeline to something like this?
Yeah, absolutely. So we don't have any type of time data in this particular example, but you can absolutely add any type of attribute that you care about. Trying to think off the top of my head.
I guess what I'm getting at is, it would have to be in the UI, but something where I could, show this for, a week and show and have the colors in the change over time.
Yeah, so the question is, could you add colors to this, or could you add some aspect of this to show changes over time? And the answer is absolutely. So the way you would do that is basically to set up some, you would have all of the data loaded for that week for in whatever time chunks you wanted to go through, and then you would set up a procedure that would say, I'm going to change the data, I'm going to change which of those attributes I want to use to drive the color and thickness and whatever of these lines. So yeah, if that was a custom function that you wanted to put in there, that would be a very straightforward one to implement.
Any other questions?
Yeah, let's say I'm using this to give a presentation, and one of the people in the room is colorblind. Is this something that would require heavy rear work to change the thing so that you use a stipple pattern or something else, or is that something that you handle how it works?
So the question is supporting colorblind user. So for this particular example, that would not be terribly easy. However, you could do something like use dash patterns, use images to indicate something along the line that would show it. You could add, instead of just having a label here that shows the total bandwidth, you could have a label that shows utilization as well. You could just scale from, a light gray to black. So it's really just a matter of approach. Really, the system is very flexible, and edges are, you could even use size of an arrowhead, shape of an arrowhead, any type of annotation you wanted to put along the edge or beside the edge. It's an extremely flexible framework, and depending on how deep you want to dive, it basically will do anything that you could dream up in terms of what you want to put in terms of any type of front end.
I have a question. So if I was interested in doing some work on like fleet logistics, is there a way to like add a map?
Yeah.
I'm just trying to wrap my head around how I would do something like that.
Yeah, so the question is related to fleet logistics. If you wanted to make a fleet logistics app, is there some way to add a map to this? The answer is yes, absolutely. So allow me to come back around to that question, and I will show you an application that has a map in it.
Is that real time? Real time?
So the follow-up question is about real time. So Perspectives is kind of agnostic to that. Either you can load a static data set, or you could use some type of WebSocket push or other architecture or periodic polling to get information either live or almost live from whatever data source you're feeding from. So like electric utilities, telecom companies often use this stuff, and they decide, if I have, these are all of my power lines, they're connected to each other in this way. That information is not going to change more than once a week, right? So I'm going to update that every week, but I need to know the status of the power lines and the power at these households, maybe every 2 minutes or instantaneously, depending on how they have it set up. So they just set up their integrators, right? So integrators are what tie your backend, Neo4j, Excel, REST data to your front end, and to your in-memory data model, which then drives your front end. And so basically you can define how often and to what degree you wish to update that data. So the other thing that I want to show while we're in here, so just like you can use NeoQuery to find a route between some start node and some end node, it's pretty interesting to know if one part of your cellular network can connect to some other part of your cellular network. So let's just pick a node up here. And we're going to call this the start node. And this is just a very simple custom action that was written here that sets is the start node to true. It's just an attribute of that data. And let's just arbitrarily pick one over here. And that's going to be our end node. All right, so let's fit this whole graph on the screen. And let's find the shortest path between these two nodes. So again, colors of those edges, thickness of those edges, all driven by data. What we have now is that the data has changed to reflect the fact that we have performed an analysis. And so now we can see the result of that analysis because the coloring of the edges is sensitive to that. And so all of these edges gray out, and here we get this route from our start node to our end node. And we can perform some other analyses as well. So let's find all the disjoint paths. So here, we can find some paths right in here. Let's zoom in. So we have these 4 disjoint paths. None of these will go over the same edge. So this is essentially mimicking, if there is a failure of a particular device on a cellular tower, none of these connectors are reliant on the same devices. And we can even walk along these paths, because that seems like a fun thing to do. Let's go ahead and walk to here. We'll walk to here. Just follow this path. There we go. Slide along over and down. This is a fun one. Here you can see that we are allowing the same node to be used, right? These both move through the same node, but the devices, the incoming and outgoing device connections are different, right? So they're using different antennae on this tower. And this path tracing is all available in HTML5 as well as in this desktop view. This is a really long path. Okay, but we made it. So we made it to the finish. And so, just one more just for fun. We can also show the disjoint path, or not the disjoint paths, the minimum cut. So let's zoom back out. And this is showing us that this is the minimum set of edges that would have to be disrupted within this network to isolate these 2 cell phone towers from each other. And if you imagine this in a slightly different context, maybe these are 2 project managers that are highly dependent on one another. And if you have, a day where some number of people are out or a certain number of people move out of the company over the next 6 or 8 months, you need to know that there are these communication channels that are not going to be disrupted. If you are in a slightly different field of work, maybe this guy this is a guy on the left who has some drugs that he wants to mule to the guy on the right. So these are important things to be aware of anytime you're talking about relationship of one thing to another. And then, way back when we were talking about circular clusters, we talked about the interconnectivity. And finding clusters within the data. So we just ran an algorithm called clustering. Looks kind of arbitrary. But in fact, what we've done here is we have found the groups such that the internal connectivity is high and the external connectivity is low. And if we were to run circular layout, we should not be terribly shocked to find that those nodes all gravitate together.
You get to choose which clustering algorithm you use.
So this clustering algorithm is specifically based on connectivity. You can tweak the parameters, right? So you can suggest that it find larger or smaller clusters and give it target sizes and maximum sizes for clusters. So you can tweak the parameters. This is just running on the default.
Can you define a cluster?
So there's a question. There's a question about what is a cluster. Okay. So the question is, what is a cluster? So a cluster is a group of nodes such that the maximal degree of connectivity exists within a cluster, and the minimum exists between clusters, right? So all of these purple nodes are more strongly connected to each other than they are to, for example, any of these blue nodes, right? And the red nodes are very weakly connected to these yellow nodes because there's not even a direct connection between these 2 clusters.
Is this a unique arrangement? Like, can there be another arrangement which has the same properties? Or?
For most real data sets, it is unique. Again, the parameters can be tweaked so that you can get slightly different results if you are getting clusters that seem too large for your purposes or too small for your purposes, or you have hard limits on what you want it to be, you can adjust the parameters. Okay, so now I'm going to pull up something with a map.
Can you show drill down?
Oh yeah, sure. So let me. Wait, does this have groups in it? This may not have groups in it. I'll jump back to network editor and show drill down. So one of the things that is often useful to do when you are talking about very large sets of data is to simplify the way you're viewing it. It's great to have 500,000 data points. It's horrible to look at 500,000 data points. So there are a bunch of complexity management techniques you can utilize, and one of them is nesting. So I'm just going to open network editor back up. And again, so we saw a network editor in HTML5 preview before. We just launched a desktop preview. It's pretty similar. Probably if I hadn't told you I was going to launch the other preview, wouldn't have thought anything of it. But here we are. So under the settings tree, I can change my group by attribute. We're going to change this to group by location. Location is just the building that it's located in. And now, again, the data just says what the location is of the node, or of the data element that represents the node. And so we're just going to create a container node that represents each of those things. So let's go ahead and collapse all these groups. So now we have a very simplified view of the drawing that just shows all our buildings. Let's go ahead and lay that out again, tighten that up. And then we can, for example, expand this site to see the individuals in this area, but only see the abstract versions of the others. Or we can even drill right down into it and only look at these individual, just look within this drawing. And the depth of this nesting is arbitrary.
Yeah. So how does it work if you have 500,000 points, as you just mentioned? Is the browser will survive? Even if you group that, can it handle 500,000 points? As you just mentioned before.
So the question is, even if you group it, can you handle 500,000 points? So the data model is handled in memory. Usually, if you've got your 500,000 points, those are going to exist, for example, in your database. And you don't want to bring them all into memory simultaneously. But what you can do is, so here we have a very simple application where, because it's small, we're just going to drill down and show where we're loading all the data, and then we're exploring it by just grouping it and drilling down, right? In the Neo example that I showed you, the Cineast example, right? We started with a very small subset of the data, and then we explored it by actually loading additional data from the backend data source. If you were going to have some group of 500,000 data points that you wanted to look at, you would start with a very high level abstraction or a very small subset, and you would explore. And that exploration could take the form of drilling down, and as you drill down, load what needs to be below it. It could take the approach we use here of finding neighbors. It could take the form of basically anything you can imagine that makes your data grow in complexity without actually, or grow in size without growing in complexity to view at high level, right? And there are a lot of approaches that we see people use. This sort of neighbor exploration and drill down are both very common.
So, like the layout and rendering can handle, thousands of nodes per drawing. Something like a symmetric could draw 40 or 50,000 nodes at a time. But it starts to, then it depends on. But yeah, a lot of people want to start at high level and drill in, or use filters.
Does it go faster than Gephi, for example?
Oh yeah.
Like 50,000 nodes. 500,000 is a lot, but 50,000 can.
Yeah, we have like a subquadrat, like our symmetric layout is subquadratic. It's I don't know if you have
I don't have a very large demo queued up, but yeah, the
Governance,
layout.
maybe?
Yeah, I can show governance. That's one that's got a pretty nice data set. Let's see if I have that one recently. No. So here's a project that shows some SEC data representing the boards of directors of a variety of companies. And you can see this is a reasonably sized data set. This is a couple hundred nodes, several hundred nodes, and you know, comes up pretty quickly. Here we can see it in a social network view, where we're going to take all the companies out of the equation and only show the connection from a person to a person. And here you can see this is a very high degree drawing. These are, this is a symmetric layout. Where the symmetric runs of about 1,000 nodes a second for a typical drawing. So if you have, you know, a 10,000 node drawing, which would be pretty high on the scale of human comprehensibility, you could lay it out in 10 seconds, right? I mean, looking at 10,000 objects and understanding what those 10,000 objects means gets pretty tough. So usually on human comprehensible scales of data, the layout is extremely fast. You know, it's not going to take more than 2 or 3 seconds for anything a person could look at and rock.
So is that thousands of nodes, and how much size is that file loading in the browser, or is it how will it structure show it?
So it depends a lot. So because these are attributed objects, right? Just like in the Neo backend, there are attributed nodes, attributed edges. So you have the data model. The data model has attributes. There are rendering attributes associated with the nodes. The more attributes there are on each of those things, the more memory it takes up. So there are very simple drawings that have, you know, 1 and 2 attributes per node, and then there are other drawings, you know, where you've got 50 attributes per node, and so obviously it's going to be a very wide variance.
What's been the one you've seen top end for best case scenario, still be rendering a reasonable time to actually?
Just in terms of layout.
File size and seconds.
Sorry, what's the question? Well, what do you think the
The largest,
reasonable?
the largest reasonable data set that we load. I mean,
Oh, I mean, well, it depends on the client, you know, as
I'm
well.
saying from your experience, like when you built it.
Oh, well, like 50,000 nodes would be
Yeah,
fine, or it's you know, it'll produce an overlap-free, like symmetric drawing.
Yeah.
So there's different circular drawing is also clustering with multiple face symmetric layout. So that's also quite similarly fast. And then we have orthogonal and, you know, hierarchical drawing. But it also depends on the data in the rendering, because there's a scene graph per graphical element, because we have level of detail graphics and everything.
Yeah,
So some of the data going over the wire.
Josh, show that in image map mode. This is HTML5, which has full animation support. But if
Yeah.
you show the same drawing, which image map mode is like Google Maps.
Or like developer view in the browser.
Yeah, exactly. Only an image here. See how fast that was?
Yeah.
Yeah, do a circular now, Josh.
Yeah, so like from the data to the drawing and through the layout.
And now go back to symmetric again.
Now back to
yeah, so these are distinct layouts running on this data set, and the reason it's running a little faster is because the browser is not doing any of the rendering. It looks the same, it interacts the same, but in fact, this is an image that's being served up by the server side, which happens to be localhost here. But
Does it do any, it's a station 5, I assume you're exporting local storage, local processing for any data you have to update and change?
Yes, all client-side rendering happens on the device itself, and only changes are communicated to the server.
Yes,
So the
lazy
server-side model is aware of all changes that happen in the client. So any deltas, you can actually fully interactively edit inside the browser. And so the server side, you can code on the server side that respects what's going on the client. And only change data is transmitted over the wire.
Cool.
Yeah, so the question was about where you can make changes and where those changes are reflected. Yeah, so only at the point where you actually make changes to the model do those get reflected back to the server. And a change on the server will only be reflected back to the database if you choose to commit that back to the database, so you can work locally. So the question is about what database. So this is an imperial in-memory data model right now. You can connect to anything from Neo4j to an XML file to basically whatever backend data source you want.
This data set here is SEC data for like interlocking boards of directors of companies. So actually, can you show some filtering, Josh?
So this was RDF
Sure.
originally.
Okay, so yeah, because we work on the Edgar.org stuff and the stuff from the Department of Energy on power value, all the land in the country and all the property. So yeah, it's JSON RDF.
So we're going to do some filtering. So here we've got this minimum degree, which is the number of boards of directors that an individual serves upon. So here it's set to 1 because we want to see everybody, but we can set this up to 3 and it will dynamically filter based on the data. So now these are only the individuals with that serve on at least 3 boards of directors. And we can just lay that out again. And it just takes a second. And here, here's the orthogonal schematic view, or the cluster view. So this data set is a social network. It's kind of an unusual social network. Social network is being like your friends on Facebook, but these are all people who work together in large companies. So they are in fact a social network because they know each other and they interact. So we can run some social networking algorithms on them. So we have a bunch of centrality algorithms built into the software. So we can use eigenvector, degree centrality, closeness centrality, betweenness centrality. Betweenness is kind of a cool one, so let's just try that. And here you can see, again, we're using, we're just changing the attributes of the data. Those attributes are reflected in the size and coloration of the nodes.
Why are they all male?
They are all male icons because we did not assign genders to anyone in this data set. This does not reflect the fact that these are all men. I don't know if that's true. Yeah, we did it for the cineast example, but this is just, this represents person. Maybe they, got their hair behind them or something, I don't know.
Probably wasn't in the SEC data.
Yeah.
They probably are all. I mean, they should, let's say they list male, female, maybe. Do they list that in SEC data? They're going on
Well, we don't have it in this data set. That's all there is to it. I mean, whether the raw data had it, I mean, we don't have it for this demo. So, but if you have it in your data, obviously, you can use it to. Right, you can use any image you want. So yeah, we've resized and laid out this data.
You said closeness. I saw that. Are you able to do using the closeness algorithm when it was the whole 6 degrees
So the question is, can you compute 6 degrees of Kevin Bacon? And that is actually a reachability algorithm, not a closeness algorithm. So closeness centrality is slightly different than that. It represents how close you are to everyone else in the network. So Kevin Bacon would have an extremely high closeness centrality if you were to load him in the cineast's graph. So here we can see within this graph, based on the betweenness centrality, we've got this Marshall-Geller guy in here. Oh, see, this one's Andrea, so that's likely to be a lady, and just got a funny haircut, I guess. So, yeah, so Marshall-Geller has this high centrality, but is closely followed by this Richard Plundiger and Andrea Cantor within this filtered data set. But you can see maybe you're not interested in just people who are high degree, who serve on a lot of boards, but maybe you're actually interested in everybody who's on any of these boards. I mean, they're all pretty important people, right? Let's go ahead and change this. Go back to the centralities, and now we've reintroduced everybody, so the graph has become a bit of a mess again. So let's go ahead and do a new layout. This was 181.55 for Marshall, Richard, and Andrea. And we're just running this again, and now you can see this has changed a lot, right? So Andrea, who was third before, has fallen down to 7th. Lawrence Chaperon is down to 77, or is up to 47. Richard has fallen all the way down to 36. And this is just a normalized centrality value. These aren't raw values. And Marshall Geller is still the most important, but he's most important by a much higher degree. So this kind of demonstrates that the ability to dynamically filter your data on the fly, even after drawing it out of the database, applying additional metrics on it can be very useful in looking at and understanding exactly what it is that you need to extract from your data set.
What is some things on the horizon? I'm sorry,
Just curious what, where, who really gravitates towards your solution here? What are the top couple of use cases? Where somebody's paying you some dollars for this solution.
So the question is about top use cases. Top use cases are in spaces like telecoms, utilities, banks for fraud detection, any kind of network management. So like, Cisco. So Cisco Prime is built around this.
And link analysis is like multiple entity types, and connecting the dots applications.
Yeah, so various types of investigative applications. For example, fraud detection, leak detection, drug muling, whatever you think is interesting data, but stuff connected to other stuff. Those are probably the biggest general markets, but we're also used, even in bioinformatics and stuff like that. I think we are running low on time, and I am going to show a map. So.
You need the internet for that, Josh?
Maybe what?
You need the internet for that.
Oh, I do need the internet for that. Google Maps is not in my computer.
The other applications where we're seeing a lot of progress now are in manufacturing design, because of our orthogonal drawing technology is very advanced. So we're seeing system modeling and manufacturing apps. So we have we have hierarchical drawing, which is nice for, we used to have a lot of software engineering clients, and but we're seeing a lot of process apps, things like that. But in the orthogonal views we have now are more advanced than what you can do with this, because we have overlap-free labeled drawings. And it's very hard to do with just like the low end of our market now is all doing just network maps, and there's another thing to go from that to overlap-free schematic representations, which we've been
AutoCAD type drawing.
Yeah, like AutoCAD or oil and gas applications, utilities, usages, modeling applications where they prefer like an orthogonal view of the data versus a network view. So it's more like a InDesign application.
Is that for your OEM customers?
Well, we have OEM and end user. So
some of the things you mentioned sounded like OEM. So
yeah, we have a lot of OEMs traditionally, but it's been changing in the last say 5 years more to sales to end organizations, which is more of our focus, just because it's easier to sell. Yeah.
So here is a Google map. This is showing some flights, domestic and international, that go into and out of Hawaii. So this is obviously a Google map. We are using the data model to populate this Google map, just like we used the data model to populate a drawing view, just like we used to populate a table, and these can be used side by side in exactly the way you would expect. Selection is coordinated between them because it's all just driven by the data elements behind it. The other kind of neat way, and I will have to be reminded if we have an example that's using this, is you can actually use the latitude and longitude coordinates of a point to either directly constrain and say, I want this on my drawing in exactly the point where this should be on a map, right? And if there are 3 miles between it, these should be this far apart. If there are 20 miles between it, they should be approximately 7 times as far apart. Or you can use geographical hinting. So if you've got offices in New York, offices in San Francisco, and offices in Mexico City, the New York offices will appear at the top right, Mexico City offices will be bottom center, San Francisco offices will be middle left, right? So you can use them using a constraint system. So we have a very powerful constraint system that applies in slightly different ways to all of our layout types. So basically, if you want to say where nodes are relative to other nodes, if you want edges to kind of flow together, if you want nodes to appear in a sequence, if you want to fix them on the map, if you want clusters of nodes to be loosely or tightly associated with one another, if you want vertical bands like a swim lane, if you want everything to be on a specific radius relative to a given point, all of that stuff is available through constraints, and you can use that to whatever degree of precision you want. Use geographical or other data to inform the positions of your attributed objects and their representations in the front end. And we've also tied in with OpenStreetMaps before and a couple other mapping softwares, but this is the one that we provide straight out of the box. It's not terribly difficult to integrate with others.
So what are some of the things that you want to do in the roadmap that you can't do directly with Tom Sawyer getting demand for features that you hadn't thought to add earlier?
So things on the feature roadmap.
We're finishing charting.
Yeah, so
we'll have charting in a few months.
Yeah, we're going to have charts. So the thing that during the Neo4j presentation we were told isn't graphs, still not graphs for us, but people like to have charts of stuff, so we're going to have charting components in there. There are improvements to the layout that are coming. So the first layout software was written 21 years ago, Brendan? Something like that, the first Tom Sawyer layout. And it's still getting better all the time. We put in a ton of work on it. We've gotten 40% improvement in symmetrical layout speed over the past 2 years, I think is what Kevin told me earlier today, based on the latest measurements. So all of this stuff is getting better. Like all the orthogonal routing is just getting tighter. We've gotten all kinds of improvements in technologies based on getting things not to overlap, which is a very hard problem with highly connected graphs. So there's always more work to be done in that space, making it faster, making it better. There's always new data sources. Neo4j was not around 20 years ago, so there are more data sources to connect to because all of your data source doesn't necessarily live in the same place. A lot of people mix and match.
Can you load simultaneously show like from relational data sources versus non-relational, like graph databases and others?
Yes, but the question was related to showing multiple data sources. And the answer is yeah. This CineS data source, the way we're getting the genders of these is actually not from like an IMDb profile or from the attributed data source that actually does not include the genders. All we have is the names. So we went and got some random data that said, what is the probability that a particular name is a particular gender, and if it's over 50% in one direction or the other, we just assign the most probable gender for that person. I think Lawrence Fishburne actually might appear as a woman, because Lawrence, as he spells it, is slightly more common as a woman's name.
I think Jackie Chan came out as a woman.
There you go. Oh no, he did show who's the guy here. But in any case,
So do you overlay that stuff, or how do you?
it all comes together as the data model. It's not, it's not an overlay. It's actually just the way that the data.
It's not property.
On the server side, you have full API control of
Right.
the model. So you can basically say new, set, just like you would a property graph. It's add, set, whatever you want, and then later you can drive your whole UI from it. So you can either drive it from an XML file, a relational database, a text file, CSV, all the kind of standard formats.
Yeah.
But you can also have full programmatic API access to the model. So you have full control over it to delete, add, remove, update, and commit. So just to inform.
So yeah, we just to kind of show you the approach here that we're using, so that you can see it. Either you can use it to directly define people, but here we've just got a model element type, right? So this is just our data type that is genders, and we've got a column that's names, and we've got a column that's genders. And we're just going to load in all of these data elements that we need. And inside of our schema, we have a person, and we have a whole bunch of data types that we actually draw directly from the Neo data source, which are things like the ID, the name, the birth date, and the birthplace. But here we have the birthday, which is actually computed from by changing the date format so that it's a nice date format for this birth value. We compute out what the first name is based on splitting the name string, and we compute on the gender by looking up the value of the first name if it exists within our loaded gender name guesses, essentially.
Yeah, okay. So how would you show like public transit? How would you use this software to show public transit information with the data sets that are available? Is there anything that you already have available for that, or is that? How much discussion?
No, because you could grab URIs or URLs, because you can grab the Next Plus data with Google Maps transit data for feed. Can you grab feeds yet?
Yeah, so the question was about
URLs, URIs,
was about grabbing public transit data, or other live data sources and how to visualize that. And so the answer is just however you need to. So I mean, it depends. What is your data source? We can access, for example, a REST interface. We have a REST integrator. So anything that's got a REST API, we can connect to.
Where is that?
So if you wanted to create a new integrator, you just click on integrators, add, and this shows all the types that we have. Composite just means that it's going to be made up of multiple integrators that are going to be used together. All right. So database actually means like JDBC, SQL, old-timey databases. Excel is an Excel file. Neo4j obviously is Neo4j. RDF, REST. Text is kind of like a CSV file or an XML.
Do you clean up? Do you get tools to clean up that, or should you clean up? We've had issues where we have to clean up stuff. That has to be, because a lot of times we do it, we have to pull it from text files.
This would not be a good way to read, like a Word document and pull out unstructured data.
Yeah, that's right. Yeah, I figured you have to structure before.
Right. That if you're doing it this way, there are methods in the API that if you want to directly bring in unstructured data and do some stuff on it and turn some of that unstructured data into attributes, we could do that. We have other products that actually approach that problem that are, I don't know that they're available right now publicly, but they are. Internally, we are working on that kind of stuff.
It's a real problem. So a lot of times, especially for the government data, city-state, we get a feed, because I worked on the recovery, and I'm an ex-Cisco guy. We help with the regional labs and then National Science Foundation Graphic Arts Lab. We have to deal with data where the repository for the government for live data is a PDF. Like, it's got the formulas there, like for the stuff we did for the recovery, like for the Fed. Two of my guys helped structure that. We had to clean up PDFs with formulas for the green score stuff, for the property, restructure all that. It was a mess. Like, we had like Bernanke's guys hitting my guys to get the GS-13s so he could bring it to Congress, so he could understand what to do. Like, it's really a mess. And the same thing with the big one we did with the disrupt, the Department of Energy did a thing with MIT, disrupt future property. They put out an API. Their API was okay, but it was still kind of clunky. So.
Yeah. We can discuss that after.
Yeah, you all saw that.
Questions? I think we're reaching the end of our time. So
Yeah.
obviously, I'm just going to put my slide up here one more time in case you weren't interested at the beginning, but you are interested now. So if you have questions, any kind of technical questions, can come to me. If you have comments or feedback about the event itself, they should go to Sylvia. But yeah, thanks a lot, guys.
And then also, I think you guys have a webinar on Wednesday, right?
Tomorrow.
Yeah, actually tomorrow morning, if you are interested in sort of technical details of Neo4j integration, I will be going into much greater technical detail tomorrow morning. I did a part 1 of the webinar that's coming up tomorrow last week that is available on our YouTube channel, Tom Sawyer Software.
Cool name.
And yeah, so if you want to check out part 1 exists and is out there. Part 2 will be coming up tomorrow, and it's at 9 a.m. Yeah, you can watch it. That one will make its way to YouTube too, so you don't have to watch it, right away. And